Assalamu alaikum. So, inshallah, today we'll be starting second lecture of chapter 2. The first one actually is just introduction, introducing to some concept of first law of thermodynamics, that energy cannot be created or destroyed. It just can be converted from one form to another, and based on this we got the first law of thermodynamics, the form of the first law of thermodynamics, that energy into the system minus energy out equal to the change of energy of the system. So the first law of thermodynamics states energy in minus energy out equal to the change of energy of this system. We spoke last time that energy in minus energy out is a form of energy transfer into or out of this system, and we said this energy can transfer in the form of heat, or it can transfer in the form of work, or it can transfer due to mass transfer. And also we talk about the change of energy of the system, or the total energy of the system. We said energy can possess energy in terms of internal energy plus kinetic energy, and also plus potential energy. Okay? So inshallah today we'll be continue actually those different form of energy of energy transfer. We said energy can transfer by heat, can transfer by work, and also it can transfer due to energy transfer. So the forms of energy transfer. The forms of energy transfer. We said energy can transfer by heat, and it has actually the symbol Q. And also heat energy can transfer in the form of work, total work, or it can transfer actually due to mass transfer if we do have flow or something. This actually energy can transfer by heat in case if we do have actually two systems that are in contact with each other and we do have a temperature difference in this case, then we can have actually energy transfer by heat. Also heat has a symbol, can be expressed actually in a specific heat, which is Q small, is called actually equal to the total amount of heat Q divided by mass, calculated in kilojoule per kilogram. Also we can calculate the rate of heat transfer, Q dot, we call it as Q dot, which is equal to Q divided by delta T, the amount of heat applied for a certain time. This is actually the rate of heat transfer calculated in kilowatt. Or we can say the total amount of heat transfer will equal to Q dot multiplied by delta T. If this rate of heat transfer is steady, is constant with time, so this means this term is constant. So in this case, the total heat transfer will equal to the rate of heat transfer multiplied by delta T. If this heat is not actually steady, is not fixed with time, it is function of time in this case, unsteady, then in this case the heat transfer should equal to integration of Q dot, which is function of time dt, integration from time t1 up to time t2. This actually in case when we do have unsteady heat transfer. Okay, so those are actually the different expression for the energy transfer by heat. Also energy can transfer by work, and work actually means we have to apply a force on a certain body or a system, and this system actually, this force should result actually in a movement or a distance, L of this body. So to have a work, we have to apply force, and this actually applied force should result in a movement of this body. So in this case we have actually applied a work on this system. So this work should equal to what? Should equal to the force multiplied by the moved distance L. We can express also the work in terms actually of a specific work. It will equal to the total work divided by mass calculated in kilojoule per kilogram. And also we do have the rate of work, which is called work dot, and this is actually called also as the power, is equal to actually the work applied for a certain time delta T, and it should be calculated, the power of the system should be calculated also in kilowatt. For the last forms of energy transfer, we can have energy transfer by mass due to mass transfer, and as we said, actually if you do have a flowing fluid, So the mechanical energy actually of this flowing fluid, E mechanical, is equal to the flow energy of this fluid plus the kinetic energy plus the potential energy of this fluid. Flow energy, which is the pressure multiplied by specific volume, this is the specific energy, specific mechanical energy of the fluid, plus kinetic energy half V squared, plus potential energy, which is G by Z. And this is actually part of the total energy transfer by mass. The total energy transfer due to mass transfer is equal to the mechanical energy plus actually the internal energy of the fluid, because this fluid may be hot or cold, so it should have actually internal energy depending on its temperature and its also structure. It may have chemical or nuclear energy, so this actually in this case we have to add actually plus internal energy in order to calculate the total energy transfer due to mass transfer. Part of this energy transfer by mass transfer is called the mechanical energy of the fluid, which is actually due to the movement of the fluid, and this mechanical energy can be converted into work through the use of any device like hydraulic turbine or something. The power of the flow, power of this flow will equal to m dot multiplied by the change of the mechanical energy of the fluid. If this fluid actually is moving from one location to another or being actually crossing a device from the inlet section up to the outlet section of this device. So those are actually the forms of energy transfer. Can transfer by heat due to temperature difference, can transfer by work due to actually applying the force and negating movement of this system, and also it can transfer when we do have mass transfer through this system. So if you look at slide number 14, you will see actually this is actually what we talk about. You will see actually we do have not slide 14, just slide 12. You will see here this is the first mechanism of heat transfer, of energy transfer by heat. And you will see here that this heat actually we should have, to have heat energy transfer by heat, we should have temperature difference delta T. You see here actually this example in this slide. You see here we do have soda or something existing in a room at 25 degrees C. So if the temperature of this soda is not 25, so won't have heat transfer. If it is, let's say, 15 degrees C, then from 15 degrees C to 25 degrees C, we can have actually a certain amount of heat transfer from the hot temperature, the hot surrounding, to this soda, to heat up the soda. So let's say the heat transfer in this case with a kind of E joule per second rate of heat transfer. If we do have higher temperature difference, if this soda is existing at 5 degrees C and actually the surrounding is existing at 25, so we do have big delta T. So in this case we expect actually higher rate of heat transfer, and in this case it can be raised up to 16 joule per second. Heat transfer in the next slide, heat is defined actually as a boundary phenomenon. So only the energy has the form of heat, can be actually transferred in the form of heat. Only energy can be recognized as the form of heat at the boundary of the system. So within the boundary, actually before this heat transfer from one system to another, it is considered actually as part of internal energy of the system, like this actually hot potato. So as it is hot, so it actually has internal energy, high internal energy. If we do have actually is existing an environment at lower temperatures, then we should have heat transfer. That heat transfer actually is part of the internal energy. So it is recognized only as heat transfer at the boundary. Once it is transferred to another system, so it is actually part of its internal energy. Okay. Also, when we do have an adiabatic system means, as we said before, that we don't have any kind of heat transfer. Moving to the next slide, heat transfer actually is treated based on the kinetic theory, which says actually heat is transferred due to the kinetic motion of the molecules at the contact surface. The hot molecules actually, the kinetic energy of the hot molecules are transferred actually to the cold actually, or low kinetic energy molecule at the contact surface between the two bodies. And this is actually the correct analysis of the heat transfer or the energy transfer by heat. Before actually there was a wrong thought that actually the heat transfer is a kind of invisible fluid, and this invisible fluid they called it actually as the caloric fluid, and this actually based on what's called the caloric theory. The caloric theory actually all of it was actually a wrong theory, because actually as we said it considers the heat transfer as flowing as actually in the form of invisible fluid, and they call this invisible fluid as caloric. But now actually they discovered actually we don't have any movement of any fluid, just we do have heat is transferred due to the kinetic motion of the molecules at the contact surface. Type for heat to transfer, we do have different transfer mechanism for heat. Heat can transfer by conduction. Heat can also transfer by convection, and also heat can transfer by radiation. So the mechanisms of heat transfer. Heat can transfer by conduction. Also heat can transfer by convection, and heat also can transfer by in the form of can transfer by radiation. Heat can transfer by conduction actually in case when we do have solids, and also in case when we do have still fluids. Also in this case we may have heat transfer by conduction. So if we do have let's say here we do have a solid body. This body actually has temperature of one surface is T1 and the temperature of the other surface actually is T2. If T1 is greater than T2, so we expect we should have heat transfer in the direction from the high temperature to the low temperature. If this body actually have a width delta X, so based on Fourier law for heat of conduction, this rate of heat transfer Q naught will equal to minus the thermal conductivity of this material K multiplied by area multiplied by dt by dx. If we do have linear relations, then we can just say delta T over delta X. Delta X is the width actually of this metal. Delta T is the temperature actually difference, which is T2 minus T1. But we said T1 is greater than T2, so this term will be negative, and that's why we should have negative sign here, because this is actually negative sign is due to the direction of the heat from the high temperature to the low temperature. This temperature difference delta T can be expressed either in degrees C or in Kelvin. It doesn't matter because actually this is the temperature difference. This key is called actually, as I said, as the thermal conductivity of this substance, calculated in watt per meter cubed. This is actually a property of this substance, of this metal. This area is the cross-sectional area normal to the direction of the heat transfer. So if heat transfer through actually this surface, so this means actually this should be representing actually the cross-sectional area in this case. So this is actually the mechanism of heat transfer by conduction. It can transfer by conduction through solid or still fluid. In some cases actually in cold countries, in order actually to reduce the amount of heat loss from a building or from a house or something, they just come at the window and they actually make actually a layer of still air or something between actually the two glasses, separating actually the inside room from the outside door. This actually still air has very low actually thermal conductivity. So they use actually a layer of still fluid to separate the heat and prevent the heat to transfer actually from inside the house to the outside. And also here it can be applied, but for the reverse, to prevent actually heat to be transferred from the outside to the inside. Okay. Heat also can transfer by convection. Heat can transfer by convection from a hot surface existing at temperature, let's say Ts, to a fluid actually adjacent fluid existing, let's say at temperature Tf. Okay. So in this case, the heat transfer will equal to the convection heat transfer coefficient multiplied by area multiplied by T surface minus T fluid. Again here, this area is the area normal to the direction of the heat transfer. This H is actually called as the convective heat transfer coefficient. This is calculated in watt per meter square Kelvin. So the heat transfer by convection is mainly function of the convection heat transfer coefficient. We do have actually two approaches for the heat transfer by convection. Here in slide 15, we do have what's called the natural convection, and also we do have what's called the forced convection. If you look at this example, we do have hot egg is existing. We are cooling down actually hot egg or something, just to put it on the table or something, and leave it actually in a still air. So in this case, actually, the hot air, the air that is contact actually with this hot egg will be heated, and its density will be reduced. And again, actually, as the density is reduced, it will just flow up, and actually the cold air with higher density will just get down. Again, it will be heated, and again the cycle will be repeated. So this is actually a kind of rotational motion of air around actually this egg. But in this case, we do have, we call it natural convection. We are not applying actually any force to move this air. That's why this egg may take actually a long time. To actually fasten this process of cooling, if we apply actually, if we have a fan, and actually we put actually this wet egg in front of a fan, so we are forcing the air to go actually with higher velocity. So in this case, we are increasing the convection heat transfer coefficient, and in this case it is called actually forced convection, because we force the air to go actually through this body and cool down this body. So this forcing the air will result actually in higher heat transfer rate, and actually will result in due to actually higher convection heat transfer coefficient in this case. The final form of heat transfer is the heat transfer by radiation, and anybody actually existing at temperature higher than 0 Kelvin emits actually radiation to another body existing at lower temperature. So whatever the temperature of a body, it can actually emit radiation, but actually to other bodies existing at lower temperature. This heat transfer by radiation is equal to sigma Stephen-Boltzmann constant for radiation multiplied by epsilon emissivity multiplied by area multiplied by T surface, the surface temperature to the power 4 minus the temperature of the surrounding to the power 4. In this case, you have to keep in mind that this temperature, as it is raised to the power 4, we do have power in this case, this temperature should be substituted only in Kelvin. Okay? And this area is the area, as we said, normal to the direction of the heat transfer. This sigma is the Stephen-Boltzmann constant, just was constant 5.67 multiplied by 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay? Epsilon is called actually as the emissivity. So this epsilon is called as the emissivity of this body. And it is actually the fraction of heat that is absorbed actually by this body from the total incoming heat. So anybody actually not absorbing all of the incoming heat by radiation, like the heat of radiation coming from the sun, our body actually accepts some of it. So we do have, our body has its own emissivity. It does not accept all of the amount of heat radiated to its body, to this body. In some cases, if we do have black body or something, so the emissivity, this emissivity is equal to 1 when we do have black body. Black body actually is a body actually that accepts all of the amount of heat sent to this body. So it absorbs actually all of the amount of heat coming to this body. And in this case, it has emissivity equal to 1. And also it's related to color. So if you do have black car or something, this means actually the emissivity of this car is high, very close to 1. So it absorbs actually most of the amount of heat coming from the sun into this car. So this may heat up the surface of this car. That's why the black car are not preferred actually in this hot weather, because it may actually heat up the car, it will heat up the air inside, so it will actually require more power to drive the air conditioning system in this case. So those are actually the form of energy transfer by heat. Energy can transfer by conduction, can transfer by convection, and also can transfer by radiation. Right, let's move to the second form of energy transfer, which is energy transfer by work. As we said, we have to have actually energy transfer by work. We have to apply a force on a body, and we have actually to have a movement of this body. Then in this case, we can have work actually applied or produced by this system. Work is also boundary function, is recognized as the boundary of the system. We cannot have actually internal work within the system. We do have only internal energy. The only form of energy within a system is called the internal energy. It is recognized as work when we do have movement of this system. Then this system actually is exerting work on this case. This work may be either produced by this system, like if we do have actually a turbine or something, turbine is producing shaft power. So it is actually like hydraulic turbine. It takes actually converts the energy of the flowing fluid in terms of high pressure, and actually it converts actually this mechanical energy of the fluid into shaft power. So in this case, the turbine is producing work. Hydraulic turbine or gas turbine is burning fuel. So we burn fuel in this case, and we do have also hot gases that actually hit the turbine blades, then it can rotate, so it can produce shaft power. So in this case, turbine actually is a work producing device. We do have another kind of devices which are work consuming devices. They need actually shaft power in order to apply this force on the fluid, so that actually they can apply change on the mechanical energy of the fluid, like pump or compressor. Pump is dealing with liquid, compressor is dealing with gases. But in both cases, actually, the main function of pump or compressor are to raise the pressure of the flow. So in this case, we have to have input shaft power to this pump to apply actually this shaft power, to apply actually this work on the fluid, so that actually it can raise the pressure of the fluid, which is part of the mechanical energy of this fluid. Type as work can be produced of the system, can be out of the system, or it can be actually consumed by the system. It can be into the system. Like this also, heat transfer can be actually heat lost from the system, or it can be heat gained actually or added to the system. In this case, when it comes to the first law of thermodynamics, we do have energy in minus energy out equal to the change of energy of the system. This energy in and energy out are the form of energy transfer, heat, or work, or energy transfer by mass transfer. When it comes to substitute actually to the first law of thermodynamics, we have to substitute actually heat or work by their sign. So that's why we do have the sign conversion. So for any system, when it comes to substitute in the first law of thermodynamics, if this heat actually is added to the system, then we have to substitute this value of heat transfer into the first law of thermodynamics as a positive value. If this heat actually is rejected or lost from the system, so in this case this heat transfer should have actually a negative sign. If the reverse actually is the work, if this work is produced by the system, so in this case the work actually will substituted in the first law of thermodynamics by a positive value, like actually when we do have a turbine or something, turbine is producing work. So in this case, its work should be positive. If we do have a pump or compressor, so in this case the work is consumed. Consumed work like pump or turbine, pump or compressor. So in this case the work actually should be substituted by as a negative sign in the first law of thermodynamics. So we have to follow the sign conversion while the substitution to the first law of thermodynamics. If heat is added to the system, then in this case we have to have actually a positive sign for the heat. If it is 10 units, we have to have actually in this law, when it comes to the substitution, we will learn inshallah later on, we have to add this value as positive 10. If it is actually negative, so we have to add actually this value to this equation as minus 10. Okay. Like actually this or the reverse actually is the case of the work. When we do have work is produced, when we do have a turbine or something, then in this case the sign of the work should be positive. If it is consumed, then the sign of the work should be negative in this case. Okay. Okay, let's move to the next slide. So let's have some insight on the differences between heat transfer, the mechanism of energy transfer by heat and work. Actually, both of them are defined as boundary phenomena. As we said, the only energy is recognized in the form of heat or work at the boundary of the system. So the system cannot actually possess energy in the form of heat or work, or cannot have actually internal work or internal heat transfer. Just we do have only internal energy. Also, they are associated with a process. So in order to have heat transfer, we have to have actually temperature difference between two systems, and based on that we should have a change in temperature. This means actually the system actually is changing from one state to another state, but actually at the same state we cannot have heat transfer. Also, if we do have work, we have to apply force to get actually a movement. So in this case, we have to have a change of a system from initial state to a final state. So heat transfer and work are associated with processes, not actually a state, not actually like properties. Properties are a state actually function, but actually heat transfer and work are process function. Okay. Also, they are called actually to be as a base function. So they are not actually depending only actually the initial and the final state of the process. They depend also on the base followed actually while the system actually is transferring from actually the initial state 1 up to final state 2. How come? So let's consider actually a system undergo process from initial state 1 up to final state 2. Let's consider actually the area. Consider actually an element here. This element has width delta V and it has height B. So in this case we can say actually delta area, this delta area is equal to B multiplied by delta V. And actually to calculate the total area we have to integrate. Then in this case actually the total area will equal to what? Will equal to integration of BdV. Integration of BdV, this is actually the total area under actually this process on the BV diagram. But we said work is actually we have to apply a force on a certain body, and this actually body has to move a certain distance x, delta x or something. So delta work will equal to F dx. To calculate the total work should equal to integration of F dx. This F, which is pressure, area dx, integration, area dx, which is delta V. So actually the work is equal to what? Integration of B dV on the BV diagram. So this is the same as what? The area. So the area under the curve on the BV diagram under any process just represent what? Represent the work by this system. That's why we call actually the work as a process function, as a base function, because actually if the process is just following another path, so in this case actually the area under this curve will be different, and we expect actually the work to be different in this case. So the work is a base function depending on the path followed from state 1 up to the final state. Or it depends actually the relation between pressure and the volume in this case. And then we can do the integration to calculate this work. Unlike actually the properties are point function. So if I need to calculate the change of volume, just integrate delta V. So it will equal to V2 minus V1. So the final state minus the initial state. We don't care actually about the intermediate state in this case. And this is actually in case of any property. Delta V, anything. But in case of work or heat transfer, they are depending actually on the path followed from the initial state up to the final state. Okay. Let's consider the different form of work that we can have. We may have actually electrical work. Let's consider the first form of work. We may have electrical work or mechanical form of work. So for the electric work, which is associated actually with the electric R transfer. So if we do have a resistance coil with a resistance R, and we passed actually a certain current through the system, then certain volt, then we can have actually a volt through the circuit. The electrical work or the electrical power in this case is equal to volt multiplied by ampere. Okay. The electrical work in this case will equal to the electrical power multiplied by delta T, VI multiplied by delta T. But this is actually in case when we do have direct current. This current actually is fixed with time, not function of time. But if we do have alternating current, this current actually is function of time. Then in this case we have to do the integration. The electrical work should have integration V multiplied by I, which is function of time dt from T1 up to 2T2, in case we do have alternating current. And as you know, we do have the volt value is equal to the current multiplied by resistance. Okay, this electrical power is calculated in watt. Okay. This is regarding the electrical work. If we move actually to another kind of work, which is actually another mechanical form of work, the other form of work are actually most commonly mechanical forms of work. Mechanical form means actually we do have a body or something, we apply force on this body, and then actually we have a movement distance S. So in this case, the mechanical work is equal to the force multiplied by this distance. If force is linear function of S, then it will equal to force by distance. If it is function of S or non-linear, then we have to do integration of F ds in this case. So let's consider the first form of work, which is the mechanical shaft power, and we can actually end up with this kind of mechanical work, and inshallah we'll continue next time in the next lecture. So the mechanical shaft power or shaft work, if we do have a shaft or something, this shaft has radius r. To have this shaft actually rotating, then in this case we have to apply a tangential force for this shaft to rotate. And in this case the torque will equal to the force multiplied by the radius, or we can say force will equal to torque divided by radius. Like to have actually the work, we said work was equal to force multiplied by distance s. The distance is here, if we do have, let's say this shaft will be rotating only one revolution. So in this case the distance is moved here is equal to what? Is equal to the circumference, which is equal to 2y multiplied by r. So in this case this should equal to force, which is equal to torque by r divided by r multiplied by s, which is 2 by r. But this is only the distance for one revolution. So if we do have more than one revolution, then in this case we have to multiply by n, which is the number of revolutions. So this r, we do with this r, then it will equal to torque multiplied by 2 by n. And this is actually the shaft work. The shaft power, which is the rate of workload shaft, we have to divide by time, so it will equal to torque multiplied by 2 by n. N is the revolution, just per time it will be n dot, we call it n dot, which is actually the revolution per second. Most of the cases this actually n is just not represented in revolution per second, it is represented in revolution per minute. So it should equal to torque multiplied by 2 by n. We have to divide by 60 if this one is expressed in revolution per minute. And this is actually the shaft power in this case. This is called actually 2 by n over 60 as the angular velocity. Okay. This angular velocity, we call it as omega, but the symbol will interfere actually with the work. But actually, you know the relation between the linear velocity v and the angular velocity. Velocity at any point here equal to the angular velocity 2 by n divided by 60 multiplied by the radius r. And this is the relation between the angular velocity and the linear velocity. Okay. So inshallah next time we'll continue the other or the remaining forms of energy transfer by work, and also we'll introduce to the first law. Thank you.